At the University of Geneva this year, we have many festive activities. The first one is the 250 years of the creation of the Geneva Observatory with, during all the year, many activities. Another event is that we have 20 years of Gaia at the University of Geneva. With this mission, it's extremely difficult to stay humble because globally we are breaking many records and many adjectives are superlatives. The largest mission, the largest CCD camera in space, the largest for ESA, the first and largest consortium ever. DR3 Geneva event presentation will have a mix of different presentations. This presentation, which will be a bit general on Gaia, but also focusing on the Geneva University activities. There will be a retransmission of the ESA event. There will be a presentation on exoplanets, on variable stars, on the classification, and also on specific objects that are studied. And finally, a presentation more on technical aspects on the big data of Gaia. Gaia is an enormous success. In 2018 was the previous data release, the DR2. And we see that during 2018 there are many articles that the community published. More than 67,000 articles were published in 2018. Now I let you guess which article was the most cited among all these articles. So this is the Gaia DR2 summary article of Brown et al. It has more than 5,000 citations. And this is not by luck, but we have now the people who proposed the Gaia mission, that's Lennart Lindegren and Michael Perryman, they receive prizes. So this year, in 2022, these two people receive the Shaw Prize, which is a very high-level, high-visibility prize. Obviously, behind these two people, there are many people. There is a consortium. This is the consortium in 2017. During a consortium meeting, there are even more people like this. We are about 450 people working on the Gaia mission. Obviously, we suffered from the pandemic. So the consortium during the years 2020 to 2022 was resembling more like this, with Zoom meeting and teleconferences. Still, with this specific situation, we were able to produce the third data release. So how does it come that in Geneva, 20 years ago, we started the mission, to work on this mission? So Michael Perryman contacted me. This is a picture. I look a bit younger. He contacted me if I wanted to take the lead of the Gaia Variable Star Working Group. And there I had the support, strong support from Michel Grenon, and also of the director of the observatory, Professor Burki. Then a team was formed. Here is the team which contributed to this third data release. But along the way, we have also many other people who contributed to that mission. That was the team in Geneva. What we coordinate on the variability processing and analysis, it is wider. We have about 60 people in this group, and they are mostly from Europe. So now we are going to the heart of Gaia. What Gaia is doing, what are we doing? 2 weeks ago, we were filming a movie on Gaia and the activity of Geneva, and there was this question, can you summarize Gaia in one word? One word to summarize Gaia. And for me, this is the census. What are we doing? We are doing a census of all objects brighter than a specific limit. And that means these objects are mostly stars, but they are also solar system objects like asteroids. They are also galaxies and quasars. But globally, we have about 2 billion stars. And in this survey, if it's systematic and global, what does it represent on the Milky Way? It is only, I should put in parentheses, only 1% of our stars in the Milky Way. Now we receive often the question, how far is looking Gaia? What is the sphere that it is probing? And it's a very difficult question, because the way Gaia is functioning is depending on the luminosity of the stars. So here is for bright objects, a Cepheid, the distance you can reach, or the precision of the distance you can reach. You have 5% precision of the distance and 10%. So we are here. This is obviously artistic or a map. And you have the center of the galaxy. And the further the star is away, the less precise you have the measurement of distance. Obviously, if you take a less luminous star, you are not going that far. So that is why it's a bit complicated to answer this question. Now, I was saying this parallel, this metaphor with census. We have this metaphor on in geography or sociology on Earth. Let us assume we have this center here and this circle, and you have the different countries with the population. The sum of the population in this circle is about 2 billion. And Gaia is performing the equivalent for stars, for 2 billion stars, and is measuring many characteristics of these objects. That is as if we were measuring every month, or sometimes several measurements per day, the weight of a person, the length of the bones, the height of the person, and where is the person and how it moves. This is a bit what Gaia is performing for the stars of our galaxy. Obviously, there are some deeper parallels you can have. So, as I was showing in the previous slide, you have stars that you don't really measure, you don't reach them, but the stars are moving around. Here, as the comparison is also strong, you don't measure people from China, you don't measure people who are in the US, but you can still get information on these people, because some of these will go, for example, in Paris to the Eiffel Tower, or will see the Geneva water jet. And so you are able to measure them, and then infer some knowledge about these regions you cannot observe. So how to perform this census? So this census is done by this spacecraft. You see the size, it's 9 meters in diameter. You see the size of people, relatively small. And you have a consortium or a group of industrial partners who produced high technological instruments. So there is a participation by a Swiss industry. You have Ruag, Sideral, APCO, and Spectratime. And it should be said that one central instrument on Gaia is the atomic clock. And the atomic clock of Gaia was produced, obviously, in Switzerland. 24 hours per day, really continuously, and through 2 different field of views is mapping on one focal plane on the CCDs, the stars which are moving. So what do we see? A star here will, this is the focal plane, will go that way, and will be measured by each of the CCD. This camera is quite large. We see also the size. I put a picture where you have people. And the number of pixels of the camera is nearly 1 billion. And Gaia is impressive by the numbers. So during these 34 months of the, which consist of the DR3 data, there is nearly 1 trillion CCD measurements. And in Geneva, we worked on nearly 400 billion photometric measurements. So we are really in the era of the big data. If we look globally at the output of Gaia, we see that it is touching many subjects in astronomy. You have mostly stars, you have variable stars, which is what we are doing, but you have also binary systems, you have measurements of radial velocities for subsample like 30 million, you have obviously the astrometric and photometric measurements, which are the core of Gaia, and you have also high-resolution spectroscopy and low-resolution spectroscopy, which is providing parameters, physical parameters of the stars you measure. You have also solar system objects which are measured. If we look now at the variable stars, we have the basic diagram of astronomy, of stellar astronomy, which is called the Hertzsprung-Russell diagram. You put the blue stars, hot stars on the left, the red star, cool stars on the right, the luminous stars at the top, the faint stars below, and you have what is very well known to many astronomers. You have the main sequence, you have the white dwarf sequence, you have the red clump. And now, because of the simultaneous measurements of Gaia, we can see how things are moving around. So this is thanks to the nearly simultaneous measurement that you get in Gaia in different instruments. The output of the third data release, this consists of many articles, and we have 44 articles and the documentation. And if you look at the contribution of the University of Geneva, we have a contribution of 19 articles and the documentation over these 45 publications. In conclusion, Gaia is an unprecedented space mission. It has produced up to now unprecedented catalog in astronomy. And these catalogs and the future data release to come will last for decades and will be widely used by the astronomical community. I thank you for your attention.
Good morning and a stellar welcome from the European Space Technology Center in Noordwijk, the Netherlands, on behalf of the European Space Agency. My name is Kai Nöske. I'm ESA's Communication Program Officer for Science, and today we are looking forward for the third data release of ESA's cornerstone mission Gaia, the billion star surveyor that has taught us enormous amounts of new knowledge about our Milky Way, our home galaxy, the life and death of stars, and our place in the universe. Thank you all for joining us. Today we have an expert panel assembled, and to my right I'd like to welcome Josef Aschbacher, ESA's Director General. To my left, Günther Hasinger, ESA's Director of Science. From ESAC in Villafranca, Spain, Europe's Space Astronomy Center, Timo Prusti, the Gaia project scientist for ESA. From Leiden, the Netherlands, Anthony Brown, the Gaia DPAC, the Data Analysis and Processing Consortium Chair, Anthony Brown. And from the Istituto Nazionale di Astrofisica, based in Padua, Antonella Valenari, the Deputy Chair of the Gaia DPAC. Furthermore, we have Connie Ertz. Connie is a professor at KU Leuven and at Radboud University, a scientist who was the lead author of one of the key papers and will discuss some of the results that came out of the data release. Now, I would like to hand over to Josef Aschbacher, our DG, to give us an ESA perspective of the upcoming data release. Thank you.
So thank you, Kai, and very welcome also from my side. Today is really an exciting day because this data release has been waited for since a long time, and I've just had a discussion with my experts, with Günther in particular. 2 billion objects or stars are to be monitored, and the data of those are being released today. And this is really incredible because it will open the floodgates for new science and for new findings of our universe, of our Milky Way. And I think this is really fantastic. I'm a scientist myself, as you know, not an astronomer, but a geophysicist, but still knowing what it means if good data become available for science is always a very important moment, because this opens completely new dimensions of finding new results and really diving very deep into it and see what you can find and what new theories and new algorithms and new knowledge you can obtain from this data. So this is really a fantastic day for astronomy, for science, for ESA, but really for all in Europe. And let me just, with a few words of introduction, thank all those who have been involved in producing these data sets. Of course, the science teams themselves, but also the engineers who have been working on Gaia in the past to put the mission together, and our member states, because as always, our science program is composed of different elements, and our member states are at the core of everything. First of all, they are funding ESA and the science program, but also they are contributing extremely important instruments or knowledge themselves through the research institutions, and of course industry, which is carrying out most of the implementation and development tasks. So really a big thank you from my side to the community which makes up ESA, and this Gaia mission being one of the core missions of the science program, and the science program being one of our backbones of the ESA activities. And this is really a fantastic day today. So thank you from my side.
Thank you very much, Josef. Günther, would you like to pick up the ball?
Thank you, Josef, for picking more or less, for sending me the ball immediately. So I'm indeed very proud to be directing the ESA science program, and the scientific program of ESA is indeed enabling scientists to take over leadership, technology, scientific leadership in a number of very important areas, from the solar system and the heliosphere to the galaxy, and then to the very far reaches of the galaxy and the universe. If I could show the slide with the fleet of the ESA missions looking at the universe, and you see as the different colors of the rainbow, the different missions that we have, and in the middle row are the missions which are active right now: James Webb, Hubble, Gaia, and so on. And Gaia is basically in the middle of this map now, and in the middle of our attention today. Thank you for the slide. Gaia is really turning the world in astronomy upside down, and the number of publications, as you may know, is skyrocketing. Every day, 5 papers from Gaia missions are published, And in the last 3 years, we have actually overtaken the gold standard in astronomy, the Hubble Space Telescope, and are now producing about 1,600 papers per year. And just in time for our meeting today, there have been two major prizes that have been given out in the last 2 weeks for things that are also related to Gaia. So I'm very happy to congratulate Leonard Lindgren and Michael Perryman for receiving the Shaw Prize in Astronomy for the development of astrometry, and in particular the Hipparcos and the Gaia mission. And then I'm even more happy today to congratulate Connie Ertz, who we have here in our panel, Jørgen Christen Dalsgaard and Roger Ulrich for the Kavli Prize. This has been given for developing of helioseismology and asteroseismology. It turns out that astroseismology is now also a very important element of the Gaia mission. And with this, I hope for a wonderful day of this data release and the splash of new results to come. Go Gaia, go.
Go Gaia, go indeed. And talking about catchphrases, you can follow this data release under hashtag Gaia DR3. You can follow on Twitter ESA Gaia, ESA Science, or ESA. And if you want to find out anything about this mission, you can go to our landing page, esa.int/Gaia. Now, to give us a rejoiner of this amazing mission, I'd like to hand the word over to Timo Prusti at the European Space Astronomy Center in Villafranca, our Gaia project scientist. Timo, please.
Good morning, everyone, also on my behalf. As it was already mentioned, Gaia is a mission by the European Space Agency with a pan-European consortium, DPAC, doing the data processing. Gaia is really designed to reveal the origin, structure, and evolution of our Milky Way galaxy. We can say that we know a lot about the universe as a big entity, from Big Bang, after a few seconds of it, what happens. At the other end, we also know a lot about our solar system, planets, asteroids, comets. But what we are actually lacking knowledge is our home galaxy, Milky Way. And that is exactly the puzzle what Gaia is going to fill. It's going to provide the information of our own home Milky Way galaxy. In order to do that, Gaia has to capture nearly 2 billion stars to measure their position, movement, and brightness. And the additional elements from this data, which are specifically in this Gaia Data Release 3, are the scientific products which are revealing the properties of these stars, temperatures, masses, composition, what type of objects they are, and much more. Let me go a bit back in time. Gaia was launched 19th of December 2013. The satellite was delivered to so-called Lagrange 2 point, which is very popular now for astronomical satellites. It's dark place, and we can observe the dark skies from there. Gaia has 2 optical telescopes, 3 instruments, and about 1 billion pixels to make all the measurements. As I mentioned already, most of the targets are stars, but Gaia captures as well objects in our solar system, like asteroids, and galaxies outside the Milky Way. And this release is really containing everything what Gaia has been measuring, a full set of data.
Thank you, Timo. That was a great overview of what Gaia has been doing, what Gaia is doing. And the other side of Gaia, aside from Gaia's home in ESA and home in the member states, is a unique collaboration, a remarkable collaboration of scientists who take care of the data that Gaia is delivering. And chair of the DPAC is Anthony Brown, who has promised to tell us something about DPAC and his work. Anthony, please.
Yeah, good morning, everyone, and welcome also on behalf of DPAC to this wonderful occasion to celebrate the 3rd Gaia data release. So the effort to produce Gaia DR3 started just over 5 years ago when we ingested 940 billion observations of 2 billion sources into our data processing systems. And in December 2020, we already provided the distances, motions across the sky brightness, and color of the stars in the form of the early Gaia data release tree. And today we present the full Gaia data tree. It consists altogether of over 10 terabytes of compressed data for almost 2 billion sources, organized into roughly 90 tables, which present the richest set of astronomical data ever published. The first slide, please. The data processing itself is carried out, as Kai said, by a European consortium, the Gaia Data Processing and Analysis Consortium, in which over 20 countries and more than 100 institutes participate, including also contributions from several partners outside Europe. There are some 450 persons involved, including scientists, software engineers, and project management specialists. Thank you for the slide. Now, the Gaia collaboration has really worked very hard over the past 5 years to bring Gaia DR3 to you today, often combining their very busy DPAC schedules with other professional but also personal demands, in particular during the COVID times. And the pandemic has obviously affected the work done by everyone. And so I really want to thank deeply all the members of DPAC for the tremendous effort they made and all the time they put in this difficult and stressful period. And so I really think that the celebration of Gaia DR3 is very well deserved for everyone. Second slide, please. Now, I want to mention specifically one person, Dimitri Pourbet, who you see his picture here, and he sadly passed away last year. Now, one of the main new components of Gaia DR3 is the largest ever catalog of binary stars, superseding everything that was done in the past 2 centuries or so. And it was Dimitri who led this task from the very start of DPAC. So this release is really a testament to his leadership and to his efforts that he put in all these years into bringing about the wonderful binary star catalog that very soon our colleagues can start to enjoy. Thanks for the slide. Now, to close, as Günther already mentioned, it's an extremely productive mission. Many thousands of papers appeared which use Gaia data in some form or other, with topics ranging from the solar system all the way out to the distant universe. And I think for many of us, in particular for the younger astronomy colleagues, it's basically not possible anymore to imagine a time where you could not look up for every star, whatever you wanted to know about it. This is how much Gaia is embedded in the astronomy ecosystem at the moment. Now, the Gaia DR3, in supplement to what we already provided with Gaia EDR3, will really provide the same ease of access to the data, but then for looking up everything about the properties of stars that you want to know. And it's this that will really unleash the full power of Gaia. So I can really not wait to see the exciting results that all my colleagues will be coming up with after using the Gaia DR3 data. And I leave you with the message that what I think Gaia DR3 represents is really a supermarket of astronomical data that we will all enjoy in the coming years. Thank you.
Thank you, Anthony. Thank you for the emotional memory of Dimitri. Thank you for your summary. And I have to say, we really live in an age of big data astronomy. If the DPAC had, with a completely unemotional face, tells us they went through 930 billion observations to create a catalog of 2 billion objects, as it was the most normal thing in the world. Thank you. And we would like to move over to Antonella Marinari now, who will tell us about what we can expect from these data, what's in these data, and what kind of science we can look forward to. Antonella. Did we lose her?
We cannot hear you, Antonella.
Let's move forward. Beatrice, could you please try and reconnect Antonella? And in this case, we would move forward to Connie Ertz. Again, for those joining us late, congratulations for being the recent recipient of the prestigious Kavli Fellowship, the Kavli Prize, which is one of the most prestigious, one of the biggest awards an astronomer can receive for her groundbreaking work in asteroseismology. And Connie will tell us now what asteroseismology is about and what it means for Gaia.
Yes, thank you very much. Good morning, everybody, for your congratulations also that I received from so many people. But let me take this opportunity to tell you something about astroseismology. So most stars, including our sun, experience stellar oscillations. They are often termed starquakes or stellar vibrations. And so these vibrations make the stellar gas move up and down, and it changes the brightness of the star as a function of time. So it makes the stars blink in the sky. And this blinking of the stars, well, it can happen with amplitudes, let's say, of parts per 10 up to parts per million. So this depends very much on the mass and the evolutionary stage of the star. Now, blinking stars do offer astronomers a very powerful tool to study their internal physics and chemistry. Huh? Think of earthquakes. You know, you all know that seismologists love earthquakes if they're not too violent, so to speak, because these allow us to understand what is happening inside our planet. And so astroseismologists actually do the same, but then for stars. So we use starquakes to deduce the internal temperature, the density, the materials inside stars, and above all, also the interior rotation of stars. Now, Gaia was not at all designed to study starquakes. It can also not do it for stars like the sun, because the sun and solar type stars have too small quakes. But it turns out to be a champion of detecting starquakes in hot, massive blinking stars. Gaia DR3 already allowed us to detect more than 100,000 of such blinking massive stars. And many of them rotate so fast that the Doppler effect shifts their frequencies into new regimes for us to study. Now, think of an ambulance. You all know that when an ambulance approximates you as an observer, it shifts the frequencies of the sound waves to higher values as the star approaches you. And so we can actually detect this in starquakes that's happening while they rotate. So this is a fantastic machine. Now, to give you some better feeling of this, we will now look at an animation and listen to some sound of commonly detected starquakes that Gaia detected. And now some real stars. Listen carefully.
Amazing.
Okay, so thank you for showing the animation and the sonification. What you just saw and heard were first 3 dipole modes, then 5 quadruple modes, of which the middle one was each time placed with sound. Now, human beings cannot hear the true frequencies of these oscillation modes. So we artificially multiply them by a big factor, 8.6 million, to bring them into your audible range of your ears. And the last 3 stars that you saw and heard, the blinking of the surface, was actually representing 3 stars where we analyzed the Gaia DR3 data, and we were able to detect the dominant quake of these stars. And so Gaia can detect starquakes provided that they have an amplitude above parts per thousand. That's currently the limits that we are facing. Above all, Gaia was not made to do this, but it can detect the dominant starquake. Now, Gaia alone does not allow us to do astroseismology because the data is simply not fast enough. On the other hand, Gaia has already allowed us to detect thousands and thousands of new blinkers with gravity modes that are rotating fast. And so along with Gaia's luminosity, which is a unique feature delivered by the satellites, Gaia does tell us where the most promising stars for astroseismology are in the galaxy, 100,000 of them. And so what is nice about Gaia is that when we use these Gaia data in tandem with specialized infrastructures, such as the TESS mission that is now ongoing, that's NASA mission, but above also the future ESA Plato mission that will be dedicated to study or to detect many, many star quakes. When we use Plato in tandem with Gaia, we have a fantastic new gold mine to do astroseismology of hundreds of thousands of stars in our Milky Way galaxy. So for us, this is really a wonderful day now that we have the time series to dive into them and study the dominant star quakes of so many stars in the galaxy. Thank you.
Thank you very much, Connie. Now, Antonella has rejoined us. Apparently, she has some connection problems. Antonella, are you able to talk to us? Can you hear us? Can we hear you?
Good morning. Can you hear me?
Thank you.
Yes.
So, good morning to everybody. For a few information concerning the stars in our Milky Way, for 2 billion stars, we deliver an incredible amount and quality of information. We have a catalog of binary stars that is 40 times larger than what is already available in literature. Concerning binary variables, we have 10 million stars, and you already heard from Connie very interesting results. From the low resolution spectra, we were able to derive stellar parameters like temperature, mass, age of 500 million stars. And from the high resolution spectra, we were able to derive an additional component that is the chemical composition of the stars. Next slide, please. In the slide that you will see now, we have a few highlights. This is the most complete full sky map of the radial velocities in our Milky Way. It contains 33 million stars. You see in black all the stars that are moving towards us, and in yellow reddish the stars that are moving far away from us. So you clearly see the rotation of our disk. And the two arrows are showing the galaxies that are satellites of our Milky Way and that have a peculiar motion, like the Magellanic Clouds with the black arrow and the Sagittarius galaxy with the white arrow. And the information, if we add the information about the proper motion, we will be able to have a 3D mapping of our galaxy, of the way in which our stars are moving in our galaxy. Next slide, please. The second highlight concerns the chemical composition from high resolution spectra. You see here the density of the stars that were measured in this way. You clearly see all the stellar component of our Milky Way. So you have the disk, the central bulge, the blue halo around. In the next slide, you see the same map, but in chemical abundances. You have in red the high metallicity stars that are part of our disk, and in blue the low metallicity stars that are in the outer disk and in the yellow. So this is the information about the motion of the stars and the chemical composition is fundamental to derive a family tree of our galaxy. So to understand which stars are born in our galaxy and which stars instead were born in external galaxy, then merge with our galaxy. This is an incredible gold mine for astronomers. Thank you.
Wonderful. So while we are still on track for the 12 o'clock Central European Time data release, the weather looks fine, upper winds are fine, the servers are up and running, and the data lines are open. I would like to go around the table and ask everybody about a fun or impressive fact that is their favorite fact to talk about. If you're on an elevator, if you're talking to relatives at the dinner table, what Gaia is about. Timo, would you like to start?
I always like to make a connection with Gaia data to something called stellar occultations. we can now make such a good prediction of the star positions that we can predict a star shadow on Earth. And we can put a telescope to observe the shadow crossing the Earth. And you can imagine that the shadow from an asteroid caused by a starlight is incredibly difficult to predict. And we have some scientific measurements which are telling us new things of double asteroids or the atmospheres of moons around planets. And this is a sort of very niche topic of Gaia. It always appeals very fascinating to me that this is possible.
Thank you, Timo. I just learned something new. Anthony, would you like to follow up?
Yes, so Timo mentioned the occultations. That's indeed a very fascinating subject. And that brings me to what I actually like most about Gaia when I try to explain to people, you know, why am I staring at stars for 10 years and tracking their positions on the sky? And it's these very precise star maps that allow these better explorations of our solar system, but also navigation of spacecraft in the solar system. The New Horizons mission is a good example of that, who used the Gaia data to steer the spacecraft from Pluto onto the other Kuiper Belt object, Arrokoth. And of course, the tracking of the stars, measuring their distances, motions, but also their properties, is ultimately what allows us to look more than 10 billion years into the past history of our own Milky Way, all thanks to just very precisely mapping where stars are and what their properties are.
Antonella.
I always find very exciting when I have to talk about Gaia to my friends to explain that our galaxy is indeed a living entity where the objects are born, where they die, that our galaxy is in connection with the rest of the surrounding galaxies that are continuously interacting with our galaxy and sometimes also falling inside it. I think that this is something that is extremely fascinating.
Thank you. And Connie, aside from the sparkling stars you study, what else makes Gaia sparkle for you?
Well, let me stick to the blinking stars because that's really my pet topic, but hook on to what Anthony just said. It's the really high precision outlook for Gaia that will bring us 10 years of data potentially. And you know, for us astroseismologists, the precision of the star quakes of their frequencies goes as 1 over the total time base. And imagine we have that for 10 years Gaia, and we can couple that to the Plato mission that will be launched in 2026. That will be wonderful. For me, that duet is really an outlook into the future. I'm very much a future emphasis person, so I really look forward to that.
And thank you for advertising our future mission. Josef, you may have a geologist, geophysicist.
Yes, in fact, I was warned about this fun fact thing. So as I'm a geophysicist, I want to merge geophysics with astronomy. And what I show you now is something very special. You see here, there's a cup of a coffee cup where you can put tea in or whatever you want. What I've put in is sand, actually from the beaches outside here in Aztec, and there are grains of sand. So now imagine that each of these data which are being released now is 1 grain of sand. How many cups of coffee you think are being filled with this data which we are releasing today? And if you add it up and do simple mathematics and a bit of assumptions of how many grains fit in a coffee cup, you will have 500 of those cups filled with sand, which is the equivalent to all the data released. So I think this is quite impressive, and I'm very happy I can merge geophysics with astronomy.
Günther, would you like to close the circle with another cosmic perspective?
Yes. Actually, this is a real fun fact that you may have heard about, but you know that Gaia and James Webb are similar in the same L2 region. They are not on exactly the same orbit. They move around L2 in different ways. And actually, every once in a while, James Webb is visible in the Gaia field of view. And so we have, a few months ago, released a picture postcard where Gaia was observing James Webb. And this was not just fun. Actually, it turned out that the position where Gaia found James Webb was about 40 meters away from where James Webb thought it would be. And therefore, Gaia can actually tell James Webb better and more accurately where it is than James Webb itself. And so we want to continue this monitoring. We want to measure the position of James Webb through Gaia. But then also James Webb has said that at one point they would do a reciprocity. They want to look at Gaia with the James Webb telescope. So I'm looking forward to that.
So we're sitting outside 1.5 million kilometers from Earth, both of them in a halo orbit of about 800,000 kilometers around L2, going around the Earth, around the sun with Earth, and they're telling each other you're 40 meters off. Also, hats off to the colleagues in operations who know exactly where probes are with about this accuracy. It's amazing. Joseph, a closing question to you. Looking at the success that I think we can, without bragging, say this mission has been, what does a mission like Gaia mean for ESA, for its member states?
I mean, what does it mean? So first, Gaia is a mission that is a full ESA mission, full in the sense of course, the member states are funding the science program and therefore the Gaia mission, but also the design, the development, the launch, the operation, all done by ESA through our partners. And I think this is something where all of us, really all of us, can be extremely proud. And I was really so impressed to hear the reports of the scientists. I mean, fantastic. Timo, Anthony, Antonella, and Connie about the earthquakes or the space quakes or astroseismology, as it is called, is really fun. It's really amazing and it's really fantastic. So this for me means really so much. I think there's so much exciting science coming out of it. I'm really impressed of what I've just learned myself today. I've really seen some extremely impressive things, and but I'm also realizing how many people are involved in making this happen. People in the member states, science labs, science groups. Connie having received the award today. Congratulations also from my side, but also many others who are working day and night in order to make this a huge success. So I'm just so impressed and also humbled by all this excitement and this intelligence which is brought together here, from science to engineering, and to really make this data release possible. So for me, this is really is very remarkable. I've already mentioned before the thanks to the member states, to all the people involved, and I really would like just to reiterate this, because this is at the core of how we function as ESA. We have a very important ministerial coming up in November. The science program is a key element of it, and whoever is watching here making decisions about this, I can only reiterate how important it is to fund the science program well, because this is what we need. And in order to have exciting moments like this, we do need the support of our member states and the community at large. So really big thank you from my side, and very impressive what I see.
Thank you. Günther, talking about the future of the science program, will there be another Gaia?
That's a very good question. First, I would like to mention one mission which was not mentioned today, which is Euclid, because Euclid is not measuring stars, it's measuring galaxies, but you can in principle regard it as a Gaia for galaxies. And when you look at the Euclid data, it will actually outshine the Gaia data by another factor of 5 to 10. So there will be more data, a tsunami coming towards us. And so we are actually learning a lot from the Gaia Deepak, how we will deal with the Euclid data. Now, indeed, the question of whether there will be a successor to Gaia as such is a very important one. And our Voyage 2050 exercise, which is looking at the next 25 years of the ESA science program, has made Gaia in the near infrared a very high priority mission, which we hopefully can implement. I mean, we have to talk to the scientific community, to the member states. But if you imagine Gaia will stop working in a few years, then we will not have any more new data. In the meantime, the stars are continuing to move. And so year by year, our knowledge of the stars will actually degrade if we don't do anything. If we could do another Gaia about 10 years later, then we could tie these two together and we would get even more accuracy of the proper motions and the stellar velocities. And this Gaia in the near infrared would then also be able to peer into the dark regions of our own galaxies. We'll be able to see the galactic center, and we'll probably see not only 2 billion, but probably 10 billion stars, because the infrared stars are more, there are more of them and they are shining brighter in the infrared. So indeed, I think Gaia has set the pace to another future for a whole generation, hopefully in 20, 25 years from now.
Let's cross our fingers for, and already say, go new Gaia again. Thank you so much to this very entertaining, very knowledgeable panel.
And the first speaker is Professor Damien Sagranson, who will talk about exoplanets with Gaia astrometry.
Thank you, Mark. I'm very, very happy to be here today to present you the first results on exoplanet candidates with Gaia, because it has been many years that my team and the Torino team have been working on the pipeline to produce the first exoplanet catalog, or low mass companion catalogs for Gaia. So we are very delighted, please. So I'm sure a good fraction of you have seen the Gaia image of the week back in January. It's the first candidate. It's not a candidate, it's a validation of the first exoplanet that we had with Gaia. So the planet was published by Alessandro Sozzetti in 2006. It's a massive giant planet of 8 Jupiter masses. And I will tell you later why those giant planets are of interest, because they are hard to form in a protoplanetary disk. And deriving the inclination of the orbit that only Gaia or direct imaging can do is fundamental to understand if those planets exist or if they are indeed brown dwarfs or very low mass stars. So here, brilliantly with Gaia, we managed to recover the orbit. The semi-major axis of the barycentric orbit of the star is of the order of 400 microarcseconds, and we retrieved the period and the inclination, and we confirmed that this object is indeed a planet. So that's a great result. So I went directly to the image of the week, but I should mention the members of the team that allowed this to happen. So we have a team split over 3 institutes. So in the Italian part, we have Alessandro Sozzetti, Mario Latanzi, Paolo Giacobi, so at the Astronomical Observatory of Torino in Italy. Here in Geneva, well, there is Barry Hall, who is doing a really hard work and fundamental work to assemble the pipeline and to make it coherent and validate, all the software part, and he played also a major role in the validation. And we have other members of my team, Jean-Baptiste Delille, Nicolas Unger, Domenico Barbato. And at ESA, we are lucky enough to have a former PhD student, type stars in the solar neighborhood. And here it's just an illustration of the kind of massive giant planets we get with Coralie. For these stars, it's a K0 dwarf, and we have 2 massive giant planets. It was published a long time ago, but we are keeping the monitoring of the target, because who knows, there might be an additional longer planet in the system. So we have 2 planets, 2.2 Jupiter masses, 7 Jupiter masses at 1,000 days. So this is the kind of targets where Gaia will play a major role to understand the inclination and eventually the relative inclination of the orbits. So here you can have a view of all the known planets in the Coralie sample that are massive enough, so more than 50 Jupiter masses, and you can see the distribution of this planet according to the semi-major axis of the period. And you can see here that there is a pretty good overlap with what Gaia will be able to do when we get the nominal, the whole data set of Gaia in a few years from now. And from this, we can derive the mass distribution of giant planets in the solar neighborhood, around solar type stars. And you see that you have an increase of the distribution of planets toward the low mass planets. Here it starts at 2 Jupiter masses, so you have a decrease here. Then around 60 Jupiter masses, you have what we call the brown dwarf deserts. And then the very low mass star start to shoot up toward the 50, shoot ups. Okay, but if you look at this mass distribution in more detail, you have a hint here that something is happening around the 6 to 20 Jupiter masses companion. Okay, so that's very interesting indeed, because what are these planets? How can you form such massive giant planets in the disk? With radial velocity, we have this problem of the sign I, so we don't know, it's an unknown. So since we have only a few numbers here of companions, so could it be a sign I effect? Just, you know, this bump, maybe these planets do not exist, maybe they exist, and only Gaia will reveal the true nature of these objects. So such a work has been initiated with Johannes Zalman a decade ago, or a bit more, using Hipparcos data, because we could do this exercise for the more massive object, for the brown dwarfs. So is the brown dwarf desert really drive, or is it just very low mass stars? So Johannes, myself, and Didier Queloz at that time did this work, and also Shai Zucker on a different sample with Tvimas, they did it. And we showed that many of the brown dwarfs, the low mass brown dwarf candidates, turned out to be M dwarfs. So Gaia will do such a thing on a much larger scale. So this is where I want to come. So I have already mentioned the team. So what did we do for the Gaia pipeline? Actually, we have two competing pipelines, one developed by Torino, one developed by Geneva, with different algorithms. One is based on an MCMC algorithm, and the other one a genetic algorithm. And the idea here is to have those pipelines run in parallel, and then we compare the solution and we select the best. So this is what we did. Actually, it should not be seen as a competing pipeline, but it's a synergy, because there are pros and cons in using both approaches. So we hope to take the best of the two worlds. So we end up with a catalog of known massive giant planets, brown dwarfs, and very low mass stars at DR3. So where does it come from? Because actually, since it's extremely difficult to get those tiny signature in Gaia, because we know Gaia is not perfect yet in terms of calibration of the data, and getting those tiny signals is super challenging. So using the main path of the data of the targets, we couldn't get the right target to search for planets. So we defined a dedicated planet, low mass companion search program. It's based on 20,000 selected targets from the solar neighborhood, and we processed these targets. So they are based on the known spectroscopic binaries, because we wanted to see if we are able to retrieve with the exoplanet pipeline binaries. So that was the first step. We have stars that are known to host planetary systems, and we also have brown dwarf binaries, because here Gaia would perform very well in getting the true mass of those brown dwarf binaries. And we also have a few field M, L, and T dwarfs. And from these 20,000 targets, we search for companions. So here I will be short, because time is counted. So a few gems from the 33 months of Gaia observation. So you may know about this object HD 114762. It was published in '89 by Dave Latham. At that time, the companion was published as a brown dwarf candidate of 11 Jupiter masses. As of today, we would say it's a massive giant planet, not a brown dwarf. But the period is 83 days, so you see here the radial velocity orbit, and boom, this is what Gaia got. So it's a beautiful orbit. The semi-major axis of the orbit is close to 2 milliards seconds, and we are in one of those cases where this massive giant planet turned out to be an M dwarf. I guess the mass is 0.24 or 0.3 solar masses. So, you know, we are depleting this bump you saw at the beginning of the giant planets. But in the second slide, you saw that still some companions remain there. We have another very interesting candidate. This one, we have no radial velocities, only a few actually. And this is the orbit derived by Gaia. You know, it's the first I would say it's the first Gaia planet candidate, I would say, because we still need some follow-up observation to confirm it. But here the semi-major axis is 250 microarcseconds, so it starts to be small, and it corresponds to a few Jupiter mass planets. So this population exists. It may be not as significant as you saw from the RV surveys, but there are planets in this domain. So as a warning, this star is very active, so the follow-up observation with radial velocity will be difficult. So I encourage the community to dig into this and make sure that this stays or remains in the planet domain. And we have a candidate that is super surprising. We don't understand it very well, but we looked at the data, at the Gaia data. They are of exquisite quality. So here we have a white dwarf, okay, G equals 13.7 magnitude, with a semi-major axis of 234 microarcseconds, a short period, 33 days. And this is in the planet domain. Look at the orbit, it's beautiful. We need to understand it. We don't exactly know how to validate it yet, because there are not that many lines in a white dwarf to be followed up by radial velocities, but as you see, there is plenty of good work to do as a follow-up for the Gaia observation. So, if I want to summarize in one slide what we did, so we started from 20,000 targets, and we obtained a bit more than 1,000 targets that could be that enter the catalog of low mass companions. So among those 1,000 orbits, we have 200 orbits, close to 200 orbits that are validated. We validated with the literature, with public data, and so on. It was a huge work because we are still in the learning phase here with this Gaia data. We could not apply systematic statistical criterion because at this kind of accuracy, we don't fully understand the Gaia measurements. But we have 17 solutions that are in the planetary domain, defined as lower than 20 Jupiter masses, 52 that are in a wide brown dwarf, low mass stars domain, and we have close to 1,000 binaries that are in the very low mass star domain. So please, if you're interested in brown dwarfs, in planets, we need the community to conduct the follow-up observation, so get involved. All the details about what we did is in the paper with first author Barry Hall that is, as of today, on archive. Thank you very much.
So now we have a series of short presentation. You will see coming me very quickly.
Yes.
When time to follow the timeline. And the first one is again by Laurent, describing about the variability pipeline.
Yeah, the overview of the processing. Okay, so I scare you here a bit, but that's globally the software pipeline we developed, where we take the data of Gaia, we clean a bit the data, because the data is certainly not perfect. It's very good, but not perfect. Then we compute a certain number of statistics. Then we have two paths, one which is using general variability detection and a classification scheme. There will be the presentation of Lorenzo Rimoldini on this. And this is using, typical machine learning techniques. So we already applied now machine learning is very standard, or that's even a buzzword. We are doing machine learning for maybe 15 past years. And we have a certain number of objects we classify. For that, we need to have a good training set. So once Timo Prusti, that you saw with the white hair just before, he said once, Gaia is the vacuum cleaner of the literature. Obviously, you can't use this argument in front of, for example, funding agencies. But I think it's also very good because you really find mistakes. I was amazed by some colleagues. Obviously, you have colleagues exceptional and they work a lot. But sometimes there is some catalogs, 90% of what they are saying is wrong. So I encountered this. So it was a bit shocking, a revelation for me, but okay. So we are trying to do better. And there we have the special variability detection where we kind of, we tune the algorithm to detect some object like, for example, planetary transits, short time scale, rotation modulation. So we have, or microlensing event, we really try to have these techniques which are extracting things. And obviously we have a kind of redundancy. So there is a dialogue between the global machinery who is doing the classification and the expert system that is trying to extract. And sometimes, very ironically, sometimes the very simple global system is working more than what the astronomers are doing. And so I was speaking of how amazing is this mission, but also the data is unprecedented. It's big data, artificial intelligence, and machine learning. And there we have the global result, if you want to summarize. We have, we take input 1.8 billion objects, and we have 10.5 million results. And you have the different classes of variables that I will explain later, but you have variables, you have AGN, variability induced by rotation, you have eruptive and cataclysmic phenomena, you have pulsation eclipsing systems, and you have other objects. And a few years ago, we did with Nami Molavi this beautiful diagram that is looking like one of these taxonomy of natural species, but for variability in the universe. And for example, you see you have planetary transits. So with what we did for this movie, that was done by one company, one stop. And here you have the light intensity, the color which is not changing much, and you have the radial velocity, their variation. Gaia, for Gaia, these variations are quite flat because the precision of Gaia is not. You need to go to Geneva Observatory and telescope like HARPS or Coralie to see this signal. And you have the planet, and so that's the signal we have. And so what happened here is very amusing, is that there is one person of the exoplanet group is not anymore working for the exoplanet group, but we had a fierce discussion that Gaia will never detect one exoplanetary transit because the variation is small, it's complicated, and the sampling is not at all optimized for detecting exoplanet. So obviously I wanted we detect at least one, so to prove him wrong. So we should never, that's the lesson, people should never say that such a project will never find things. And here, in fact, we have two now. They are published. And you have this the signal here. So you see it's not very dense, but it's good enough. And they were confirmed. And so there is also now a collaboration with the TESS mission that is ongoing, because in the TESS is producing is optimized to detect exoplanetary transit, but they have a problem with the PSF, the way the light is spread. And with the help of Gaia, in 10% of case, we can either say it's wrong or it's confirmed. And so we contribute to this. So we go to eclipsing binary, and we have the second movie. And again, with this little company, we produced the little curves here, where you have the light curve, and we have the color variations, and you have the radial velocity. So when you have two planets, there what you see is that you can detect the radial velocity of the two. And so that's an example of what we are able to detect. Obviously, what you detect in Gaia is just a little spot which is getting a bit dimmer. And so globally, we detect 2 billion eclipsing binaries, and so there will be a presentation dedicated to this by Nami Molavi. Then we go microlensing. Also, Gaia is not at all to detect microlensing. That's the microlensing. That's something like this. There is not much change color, and there is not much. And so that's what you have. So that's, in the case you have a microlensing, it's a black hole. So it's getting brighter when it's aligned. And so in that case, in a way, microlensing is fantastic because it's the only way you can detect black holes, single black holes. So we hope that with Gaia, we will be able, that we detected microlensing, but we didn't detect microlensing with black hole yet, but that's the goal. So that's why we need to have the DR4 and DR5. Globally, we have 363 events detected, and the work is done by Łukasz Wierzykowski in Poland. Ah, yes, this one. Here is the map. He prepared a map where you have the microlensing happening there. So suddenly you have the microlensing, so that means you have this alignment of dense objects you don't see with the background, and then it's becoming brighter. So that's the first time we have a microlensing event over the whole sky. Then we go to other population there. That is a spotted star. And so you have a star, and because the star has spots, the intensity is changing. Color is changing a bit, maybe sometimes even not in the broad band, and the radial velocity at the precision of Gaia is not changing much. So globally, with the Gaia data, we are able to detect all these. And globally, we have the largest catalog of a spotted star, that's 500,000. Then we go to the next, you have pulsating objects. And so the star in a radial mode is getting inflated and deflated, and it's changing this, its temperature. So here the light is going up and down, and you have like a hysteresis cycle on the color intensity diagram, and you have also the radial velocity. So there again with Gaia, we are kind of breaking records, and we are able, that is the image that Connie Arts wanted to show, that I included, where you have the main sequence, that's more for specialists, and there you have Gamma Dorado stars, you have Delta Scuti stars, you have SPB, and you have kind of a new harvest, a new population, which was already seen, for example, work of Nami Molavi, but also by others. There were a discussion. Now we have this group. It should be investigated, so this is good for asteroseismology to see if we can confirm this kind of discovery or not. And then, okay, we go to the supernovae. Also, we discover supernovae, and there are 3,000 supernovae. We have a little, that's very nice. The star is exploding. And this is an example, you see, that's very good, because that's a very good example, because something is changing, getting a lot brighter, and after you don't have measurements of Gaia. And then you have again. And so from this type of the curve is more like this, but you have a sample of it. And so that's the trick of Gaia with this sample to do this type of classification. Globally, we have a HR diagram. This is a beautiful HR diagram from the Large Magellan Cloud, where we can now map the different population of variables. So there is also, we have a citizen science project starting that Chris will speak about. And the whole message here, future is bright. We hope to reach 100 million variables for DR4, and that's finished.
Good morning. So I will present a brief summary on the results of the classification of variable sources from Gaia. So of course this was possible thanks to the work of many people, so I can't name them all now, but so this paper will become available during this summer. So this is just a very oversimplified sketch of the pipeline, just to show where classification is. So it receives objects as an input that have already been detected as variable, and then they have some general characterization for the sources, including some basic modeling, and then classification processes the sources, and the result of classification are then used by subsequent processing modules that look into more details into the analysis of specific classes. So Nami Mulavi will say more about this. And the main method that we use for DR3 is supervised machine learning. And so this is basically that you need to rely on what you know. So you gather a number of known data, and then you can put this data, you use it to train some classifiers, and then you use the models of these classifiers to classify basically the unknown data. And so we have these three steps. So the first one is training, and it is essential to have a good knowledge of what is out there. So we did an extensive cross-match of variable sources, and we cross-matched them with Gaia. And so we have millions of sources that were cross-matched from 150 catalogs. We have about 100 subtypes of variability. And so there is already a paper that is published about this from Panos Gavras, and this I'm sure it will be useful to the community also to be able to know this cross-match. So once we have these sources, we need to select them. So for each class, we look at which catalogs are the most reliable, which sources are where they should be, and then we select sources per class. So it is a very long work, but in the end, it is really necessary to give a good training set. Then we characterize the sources for each class with some metrics that can include from time series statistics in all the three bands to astrometry, the periodicity, and other things. And finally, we can feed all this information into the classifiers. So we train them using basically mostly two algorithms, which are random forest and extreme gradient boosting. But there is really it's difficult to know a priori which one is going to work best for which class given the data. So we use this approach of having many classifiers. So we produced over 100 classifiers that included multi-class classifiers, so 20, 30 different classes at the same time, or just two classes, binary classes, one class versus everything else. Some classifiers tried to make the best out of other classifiers. So in the end, each classifier gives a different perspective on the data. And so this helps us just to maximize the amount of information that we can use. Then we just feed, we have these models and we apply them to the data. We have this automated step where all the variable sources are classified into many classes. So, but we should not trust the results as they come out automatically. We should always verify them. And so it is important to select for every class which sources are actually going well. There is always some threshold below which there is just a lot of contamination. And also we select the classes that are really publishable because Gaia is not perfect, cannot predict every class yet. So maybe in DR4 and DR5, of course, there will be much more data. And then we combine all of these per class results and to have a single class for every source. And then we assign a classification score to each of them. So in the end, we published 10 million variable sources that were classified into 24 groups of variability types. And in addition, also 2.5 million of galaxies that were identified by the variability in the data, but it is not the variability of the galaxies themselves because it is just a spurious signal which is in the light curve of extended objects. So Barry Hall is writing a paper about this. So the classification results, so this is just a histogram of how many per class. So we have from millions, from the long period variables, Christian binaries, and so on. And we go down to a few hundred of the most rare classes. And so something to note is that the galaxies are not published within the variable classifier result as all of the other variable sources, since they are not real variables. So they are just published in a meta table, which is galaxy candidates, to which many coordination units within Gaia contributed. Okay? Okay, so now I have just a set of slides for several classes. Time will stop me. So just they will all be the same diagram. So basically we have a sky map in galactic coordinates, then then another plot that shows the intrinsic luminosity which grows going up, and the observed color which gets brighter as we go to the right. And then the last one is related to the variability of the source. So variability creates standard deviation which grows going up. And the median magnitude, so the apparent brightness goes fainter as we go right, okay? And then some sample light curves. Here they are color-coded. If it is periodic, it is color-coded with the time, which is just line down. Okay, so this is, okay, that was a group of many classes that are not necessarily physically related, but the classifier just could not split them. So we needed it because otherwise they would have ended up polluting other classes. So at least this reduces the contamination of other classes. We could have thrown them away, but we still think that it is good for the community to have some classes like this one, which even if it is a mixed box of many classes, they can find interesting things about this. Thanks. Okay, so Alpha Cygni stars, so I will go now quickly from now on. So you can see, okay, this is a much more rare class, very bright objects. Some of them have some kind of multi-periodicity inside them. Okay, this is so actigalactic nuclei. So basically these are AGNs or quasars or so-called, so there are really many of them. None of them should be in this plot, but as you see the score, this is the diversification score. This is almost zero for just a handful of sources. So for the rest, we can see the long-term variations in the light curves and so on. By the way, I did not mention this white line is the general limit for DR3 for variability, typically, not always, but most of the cases. Beta Cepheid stars, so these are very bright objects, and okay, you can see some light curves. Okay, then this is another mix of eruptive stars, the Eldorado Wolf-Rayet stars. So you can see in time that sometimes there is nothing, and then there are eruptions. It is very irregular, and yeah. So Cepheids are very important stars, used especially since the beginnings for distance determination, and they have very nice light curves. They're very bright objects, and this is a fundamental delta Cepheid. Then we have other anomalous Cepheid and also type 2 Cepheids. So they lie mostly in except for the type 2 Cepheid. Cataclysmic variables. So this is another sort of stars that can give some eruptions. So these are basically here we have between the white dwarf sequence and the main sequence. So we have cataclysmic variables with eruptions that occur just at irregular times. Then delta Scutis, so these are also are pulsating stars. So we see very nice periodic light curves. And let's go to the next slide. Eclipsing binaries. So Nami Murabi will speak more about them. This is a type they can be very sharp, or a bit smoother, or even almost like sinusoidal-like. And the ellipsoidal variables, so again, here we have the shape of the star is ellipsoidal because of its companion, and so okay, we have sinusoidal-like light curves because what we see as light is what the area that is projected. Okay, now we'll see just exoplanets. That's what Laurent mentioned earlier. So this is just between 1% and 2% of the detection. So you can see these two groups of when there is a planet that is transiting in front of the star. So you see these groups of detections. Long period variables. So they are really very red objects that have very large variations. And the microlensing events. There are some of the candidates. So this is a beautiful one where you can see the shape in time. And Arcturine Borealis, so these are other rather irregular type of stars, but you can see that their magnitude changes really drastically. And other lighter stars, they are also pulsating, so we have nice periods that are usually less than a day or so. And the next one, Ares Canum Dinopicorum stars. These are more complicated stars. But you can see, for example, how also they change in time. These points are early on, and then they become short-term scale variables. So this is another experimental class that really has inside many things that have short time scales, and some of them are encryption binaries, also like the EW type that has like contact binaries are also in there, and but it is one of those experimental boxes for the community to explore. And then some of these stars, so these are really complicated. So we have at the extreme horizontal branch we have some stars that they are pulsating, but the period in most of these diagrams is either incorrect or we have a lot of multi-frequency. And then to finish, supernovas, as well already mentioned, from nothing, we have explosion, and then it becomes detectable, and we observe the decline of it. And solar-like stars were already mentioned then. And then we can go Zoe pulsating B stars. Yes, so that is in the upper main sequence. Let's go quickly. Symbiotic stars, yes, these are very irregular in time, also have large variations. And finally, pulsating the white dwarfs. So we can see, so they are all on here. So we have 1K, this is a good period, but in the other two cases, I don't trust period. And from the Gaia data, sometimes it's just not enough to get the right here. These are young stellar objects. Some of them might be even periodic, but usually they are not, so they have kind of irregular variations. And finally, we have the galaxies. So these are not real variations, but the variations that you see in Gaia. You see they can be also rather big, but at the same time, it made it possible for us to detect them. Okay.
Wonderful, thank you.
So once we have processed the data, and as Lorenzo has shown, we classify the variable objects into specific variability types, Gaia can provide us a lot more information on it because of the many instruments, different instruments it has. So one of the goals is, once you know what type of object it is, you can study it much more in detail, knowing its properties that it will have. And this is the specific object studies that I will shortly present. So as you have seen, stars, they are variable in their photometry due to many different reasons. Reasons can be pulsation of the star, it can be rotation, like as well in the sun if you have spots on it. It can be eruptive, you have flares or things like that on the, it can be cataclysmic, the supernova are cataclysmic. It can be secular, that's a very tricky part where you see the variation of the star in time through its photometric evolution of a very long time scale. And then you have also other effects that can impact the photometry, the light that you see from a star that is not due to the star itself, but to outside conditions surrounding, like in a binary star, when one is eclipsing another one, or in the case of microlensing, where the star actually doesn't know that the person who is on Earth would see its own light varying because of the presence of another. So at each data release, we increase the number of specific objects, variable stars, for which we dedicate a specific study and we release the data in specific tables. In the case of DR3, we have 10 specific catalogs, 10 catalogs for specific variable stars, and an additional one for extragalactic, which is galactic nuclei. I will focus on the stars in this presentation. And I show here the various variability types, and I put a little flag of the country where the leading person acts. Of course, it's always a team, but there is one or two or a small group who actually leads each effort, and those people are specialized in their variability type. And we see that we have a number of objects which are published in the catalogs, and as Laurent said, the numbers are just amazingly large. If we take eclipsing binaries, we have 2 million long period variables, we have also about 2 million. Those are much more than what we currently have now in the literature. Okay, and for a total of 5 million for specific stars that are published. As I said, we increase at each data release the number of variable stars. So in DR3, we have these ones highlighted in white, which are new and that were not present in DR2. For the other ones, they were already catalogued in DR2, but with a much larger number of data sets and less properties analyzed for each star. So really at each data release, we increase not only the number of objects, but also the properties. So I will now give a brief overview of two of them, and I take the two largest ones, about 2 million, the eclipsing binaries and the long period variables. It happens that those two are also managed by people here. So the first one is the eclipsing binaries, managed basically by these people, plus the help in Geneva, and we also have contributions from outside Spain, United States, and Israel. So this is the distribution on the sky of all the eclipsing binaries, the 2 million eclipsing binaries that are published. You recognize it. This is the galactic plane. So you see the center of the galaxy, the plane of the galaxy, and these two are the external galaxies, which are the Magellanic Clouds that are very well visible from the southern hemisphere. So briefly, these eclipsing binaries, they can come in various forms. There are two stars, they orbit each other. In general, you can have three configurations. Either the stars are far enough from each other not to impact the geometry of the other, or very slightly. The second one is when one of the two stars fills what we call its Roche lobe, which is the area in which the matter is gravitationally bound to the star. But if the matter goes out of this geometry, then it's either lost in the interstellar, or most often it is transferred to the second, and that will lead to many specific phenomena. And the extreme case would be that both of them lost their Roche lobe and they actually form a common envelope. And each of these types will give specific photometric variation signatures. Now, I shouldn't say why the binaries are of interest. They are very interesting and important in astrophysics. Most of the stars actually are in binary systems. And they are kind of laboratories, because once you know properties from the eclipsing binaries, and in addition, if you have also radial velocities, then you can characterize the physical properties of each star, and this is amazing because you know exactly what star you have. And of course, they also have impact. Those are the precursors of supernova of type 1a, which leads to the expansion of the acceleration of the expansion of the universe, dark energy, and so on. And these are also at the origin of the signature that we can detect through gravitational waves currently. So that's a huge thing. So the photometry can lead to variations due to either the eclipsing binaries, or they could not be eclipsing, but if you are in one of these cases, you have an ellipsoidal variation, you still have a variation because you see a different geometry phase on you, whether you see the star like this or like that. Here are a few examples of the 2 million light curves. I just took a few ones which give different properties. You see here the detached ones. So each one or the other eclipses the first or the second one, and you see that in between the light is constant, nothing special happens. But if they are close enough, there can be a variation because the star geometry is deformed. And you have another one here. The depths are different. That tells you that the luminosities, the surface temperatures are different, and you can characterize them. And here you have more extreme cases where you have deformation, probably in semi-contact or full contact, and these lead to characterization of these properties. The periods that we currently detect range from, in this catalog, 0.2 days, so it's very short, up to several tens of days. But basically, we get currently the short periods systems. Okay, so this is the HR diagram, has already been introduced. It's an introductory slide for the purpose I want to show just after. It shows here the color and the intrinsic luminosity. You see that's a 10 million sample of the Gaia catalog, everything constant and so on. And you see that stars are usually distributed along a line The redder it is, the fainter. The bluer a star is, actually it is more massive and it is brighter. And you have this evolution track. One solar mass track is here. Those come from the Geneva models. We are somewhere here, and later we would move towards red and giant star. So this is the structure of the main sequence. That's where most stars burn hydrogen in their core. And then here you would have burning of helium. Now, from the previous graph, I put these contours of these 10 million standard stars. And in color, I put the distribution of the eclipsing binaries. Now you see that it is shifted above, right? Now, if you remove 0.75 magnitudes, you fall back to the same distribution as you have for normal stars. Why is that so? Simply because you have the two stars. So when you see the stars, actually the light that you see is twice, if they have equal masses, it's twice the luminosity of one star. So obviously, the light that you would see would be distributed more luminous, and 0.75 magnitude corresponds to twice the luminosity. And then we can do all kinds of stuff. Here, for the set of eclipsing binaries, we have the distribution of the periods. So red is more period, 0.2, blue is 5 days, and you see that it follows nicely a region dependent actually on a distribution of mean radius of stars due to the orbital motion. Okay, now, next 5 minutes, a summary on the long period variables. Again, this is different people who were contributing. That's the distribution of, on the sky of the 1.7, 1.8 million long period variables. We see that we have the galaxy as previously. We have again the Magellan clouds. Those are easy. But we also see that in the catalog we have additional extragalactic sources. For example, M31, the Andromeda galaxy, is obvious here. The Triangulum galaxy, M33, and there are a few other ones that are there. Also prominent is this Sagittarius dwarf galaxy that comes out and that is currently interacting with our galaxy. So with the LPVs we can follow that, and actually the properties of the LPVs there is distinct from the rest of the population, so we can use them to study them. Their ages are also different, so we can trace the ages of different populations. Yeah, this is a zoom on the M31 showing the different period variables. Okay, coming back to this, the long period variables are in this region, and why they are important for two things, many things, but two things is that in these stars you have nucleosynthesis operating in the core, like in many stars, but very specifically for these stars there is a very subtle physics going on that takes this carbon that is produced inside and brings it to the surface. And that's carbon, that's the carbon production and ejection. And actually, currently, the carbon that we are formed, that make us, we are not sure yet where it comes from. It's either from the massive stars when they eject them, or from these low mass stars in the carbon stars. And Gaia, providing a census of carbon stars, will allow to make one step further in this question. And there's also another part, because they are pulsating, they give period luminosity relations, and they help to estimate distances. Okay, I want to show this because that's another power of Gaia that it shows. Up till now, we have discussed about photometry, but one of the instruments of Gaia is spectrophotometry that can give you spectra. And you see here a difference between an oxygen-rich and a carbon-rich star, where the absorption features, the absorption lines are different because there are different molecules when it's carbon-rich or oxygen-rich. And we use that in DR3 to classify whether it's a carbon or oxygen-rich star, because typically, for example, the distance between two peaks in the carbon-rich star is larger than in the oxygen-rich star. And we use that. These are typical examples of light curves where you see long periods, that's 200 days. And you have different types. One thing I want to mention here is that some of them are quite clean, I would say, and some of them are kind of
noisy. It's not noise. It's simply because these stars have more than one period. It's multi-periodic. So from this and in DR4, we will aim at characterizing more than one period. And with these periods, if we put the periods as a function of luminosity, we see that there are relations. These relations were already very well known from the Magellanic Clouds, from surveys in the Magellanic Clouds, because that's easy. You have a Magellanic Cloud, you know its distance, so its intrinsic luminosity is known, and hence they could analyze it. This one is from extragalactic. Those are all dwarf galaxies in the local group outside our galaxies, and this shows that Gaia is able, this is the gray, the spheroidal dwarf galaxy, and these are the other ones, M31 and 33 and so on. So that's one interesting thing. The second interesting thing is that despite we know very well these period luminosity relations from the clouds, for which we know the distances, strangely, we don't know whether these period luminosity relations are the same in the galaxy or not, simply because we didn't have the distance. And Gaia is providing the distance, and this is the very first diagram, such diagram that we can build thanks to Gaia of the period luminosity in the galaxy, and we see that there are relations. Now, for the next months and years, community can study them. Coming to the end, yes, I just show this outside the ecliptic binaries and the long period variables. These are radial velocity time series, just to show the power of Gaia also to analyze the radial velocities. There are a few thousand ones published in DR3 for Cepheids and R Lyrae, and that's true for Cepheids. And I think the last slide now is to show to summarize the power of Gaia. It has photometry, spectrophotometry, spectroscopy, and astrometry. And just taking the example of long period variables, in DR2 we used the photometry and the integrated spectrophotometry, which is the color, and we had 150,000 sources that were published. In DR3, with the same data, we have an order of magnitude more compared to DR2, and plus we use the low resolution spectra to get the carbon stars. And for DR4, we can, in addition, compute multi-periods. Of course, we will have that as well, but we can also use the radial velocities that will characterize them. They have variations of several kilometers, tens of kilometers per second, astrophysical parameters, for example, for the extinction, and the parallaxes, so we can classify them in the subclasses according to the period luminosity.
I mean, we have to stop.
I stop.
Thank you. And we have the DPCG manager, Chris Nenartovic, who will talk us about Gaia and big data.
First of all, when we have a data, especially data like we have, which is time-oriented, we have to do something to compress the time. So we have to do some kind of time dilation to basically compress it, to make it operable by us. And we know that humans are creative, but quite slow. So if it comes to calculations or deriving some quick mathematical information or applying algorithms. But we also know the machines are fast, but are rather simplistic. Even if you talk about artificial intelligence, machine learning, all these buzzwords really, if you look deeper, need very careful human care. So for example, when we speak about speed of the machines, for our processing, we estimated that we run roughly 2.2 million CPU hours in our cluster that is hosted in observatory a few kilometers away, which would be transformed to 250 years of single core computing. If we use a normal computer, we compress it to 62 years. But our final run, when we process roughly 2 billion sources, 2 billion stars, was 16 days. But it took then 1 day to have our final run when we processed this 10 million sources that we exported. And we also, the humans run the software. So we have something called run. Run is basically your configuration, your software, and the data. And we have a dozen or more people running this software, and they execute roughly 5,000 runs for DR3 to have all these results. And Then we have 6 months roughly to fit into the window that we have from the consortium to get the data out. And so Lorenzo presented 10 million classes or sources, but in fact we had over 6 billion classification results, because we can. So our scientists basically created a lot of classifiers, and in the end we had to select 6 billion sources that we had to compress, cut down, and select the best ones that are in the end 10 millions. If it comes to big data, it's good to remember the definition of big data, because it's a buzzword. The notion of the big data was established roughly like 15 years ago, and it's good to use something called three V's. So one V is volume, and then it was adopted by the kind of data community, and this volume means that we have a lot of data. So this is clearly a case for Gaia, or for us. We have roughly petabyte amount of storage, trillions of numbers. But then we have variety. We have tens of classes, as you see. Each of these classes that Nami and Lorenzo presented, special cases, general classes, needs specific data, specific format to store. So this adds another vector of complication. Then we have, all of this is in the time series domain, so there's not that many systems. They emerged right now, last few years, but there's not that many systems that actually deal with the time-oriented data. We had to devise it from scratch, more or less. And there is velocity, so how the fast data is changing. We have these cycles that when we process, and we have to adapt to this cycles. So the formats change, the more data come, we want to do more. We have velocity, we have to cater for. And then we have the fourth V is mine. It's a victory. We actually did it. So with a relatively small team, with relatively small equipment, we did it. So I'm very happy for the small victory. And how to do this? We have to learn how to not to do things, certain things. We have to learn how to say no. I have personally problem with this, as our team knows. But we have to cut, so we have to process only what's needed, because our CPUs, our machines are still slow. If we really load data at them, it's very easy to saturate. We could jump from this 2.2 million CPU hours to 200 with no problem. We've changed in 2 lines of the configuration. We have to optimize how to store and get the information from our storage. Then we have to automate, but it's very hard to automate as humans. We want to have repeatable science, but humans don't like that much repetitions. They get tired. So we have to kind of make a balance between humans, the freedom, scientists' freedom, and what we need as kind of repetitive, credible science. Then we have to, when we have long projects like this, we have to foresee what kind of technology from hardware to software will be viable in a few years, because this project is already 15 years old. And this means we have very small margin for the error. So again, I'm very happy for victory. Then what we're doing is really converting from information that Gaia gives us. In fact, it's not only Gaia, it's other data processing centers, other collaboration units scattered all over Europe. But it's about transforming this, all these pictures, all these animations you've seen. It's a lot of work. And we have this petabyte challenge. We have this lot of years of polyglots, so we're using many languages, many kind of technologies to do this. We have to do this repetitive process to capture the knowledge. And we want to have this self-descriptive system, so we don't have data, this meta information that we generate when we obtain results all over the places. We want it in one place, so we can easily go back and understand what happened. So this means that this is, for example, this is one of the examples that I will show. This is the animation that we did. we also need, we have so much data, we have so many classes, it also means, and we are small, we are constrained by budget, by the time, so we want to look out for help. And my company Sedna was selected by ESA to help with this, so we were awarded the Gaia Citizen Science Project, so this is first Gaia Citizen Science Project. Citizen Science is the effort, or kind of shifting effort, or welcoming people from outside, not necessarily astronomers, but also amateur astronomers, students, anybody who's interested in astronomy help, to come and help. And I'm happy to announce that we got this project. It's going to start in December this year. Yes, we're going to do a lot of reaching out, PR, so I hope you're going to see it on the social media. It's called Gaia Vari, and there's already a website called GaiaVari.space. I will, in the corridor, actually, there are some movies related to this. So this is the other movie, and please with sound. That's it. Thank you. Okay.